I think we should just get started. Let's bid welcome to our final speaker, Sorrachai.
Thank you very much for staying around until to the very last talk. I'm Sorrachai. Today I will tell you more about the problem called kECSS connected spanning subgraph and how to approximate it using fast LP solver. And this is joint work with Parinya Chalermsuk, Chien Chung Huang, Danupon Nanongthai, Tachapon Saranolak, and Patara Supaser. Okay, so let's jump right in. So let me first define the problem, kECSS connected spanning subgraph. First of all, a graph is kECSS connected if it remains connected after removing k-1 edges, or like the min cut is at least k. So that's what I mean by kECSS connected. And the problem definition is the following: give you a undirected graph and a cost function on each edge, and the output we need to compute the min cost kECSS connected spanning subgraph, meaning that compute a subgraph that is spanning, that contain all the nodes, and also compute that has to be kECSS connected, and I want to minimize the cost. For this problem, when k is equal to 1, it is kind of easy to solve, right? Because one edge connected is a tree, so this is minimum spanning tree problem. But the problem becomes APX hard as soon as k is at least 2, even on the bounded graph, bounded degree graph, and binary cost function. And the best known approximation for this problem is 2, which is known very long ago. And the kECSS connected spanning subgraph is a special case of the survivable network design problem, which is a much broader class. So in terms of the complexity of this problem, for the case of very small k, let's say for 2 kECSS, you can do 3 approximation in the quadratic time. And for general k, you can do also 2 approximation in MNK, or you can do something like 2k-1 approximation in quadratic time, and so on. But and also there's a algorithm by Jen that gives like 2 approximation that solve much broader class, not just a kECSS. And today I will tell you more about the new result in this area, meaning that we can show that you can give 2 plus epsilon approximation if you in nearly linear time, if you can output only the estimate, output the value. But if you want to output the solution, it will need some more time addition, like n to the 1.5 times k square over epsilon square to get the integral solution. And the key main technique is that we just solve the LP in nearly linear time, and then we do the rounding. So let me talk about how to solve LP for this problem. And okay, so here is the LP formulation for kECSS problem. So I want to minimize the sum of the cost on the variable xe, and then we want to select each edge such that for each cut it cover at least k amount for per cut, and then there's a restriction that you cannot pick more than one edge. So there's an upper limit on the box constraint here. And for the purpose of this talk, when I say cut here, I mean the set of edges instead of set of nodes. So for example, when I say cut AB, it means literally just 2 edges there. And how fast can we solve this kECSS LP? You can solve it in mn time over epsilon square by Fleischer very long ago. And it turns out that if you want to solve there's a slightly easier problem, which is called kECSM. If you can remove the box constraint, meaning that if you can select multiple edges, then this problem is called kECSM, kECSS connected spanning multi-subgraph. And similar LP can be solved efficiently. And the LP is exactly the same, except that you don't have box constraint. And the key recent work by Chekuli and Conrad give this say that this particular LP can be solved in nearly linear time. However, the framework cannot handle the box constraint, and the key contribution of this work is basically we show that the framework can actually be extended and solve this box constraint. That's the main message. Okay. Now, what are some applications of this? What is a useful utility of the LP solver? So we can use it to estimate the optimal integral solution within factor 2 because of the integrality gap is 2 in this case. And we can also use this to get the integral solution that is running time of this form of m over epsilon square plus n to the 1.5 k square and epsilon over epsilon square. But the key approach here, we follow the standard template that also even outlined in the other works, that we solve the kECSS LP up to 1 epsilon accuracy, and we specify the LP solution using some form of graph compression theorem from Benzo-Karger, and we show that we can specify the graph so that the number of edges is of the form k square n epsilon minus 2 to the minus 2, and then we run the combinatorial algorithm by Khuller Vishkin on the support of specified graph, and hence we get this kind of running time. But for today, I'm more interested. I want to focus on how to solve the LP LP solver in nearly linear time. So I want to focus on this main result. Now, next, I'm gonna talk about the multiplicative weight update framework, and I want to highlight the key challenge that appear in handling the block constraint. Okay, and I know that everybody is familiar with this framework. I want to phrase this in a language that we know, that in a common language here. So let's take a look at the covering LP, the general covering LP that minimize C transpose X such that AX at least 1. Now one can think about this as a very tall matrix, implicit matrix, in a sense that the number of rows can be exponentially very large, and all the entry is positive. So I want to solve this covering LP, and the standard multiplicative weight update framework from Garg and Kahneman says that, well, you can reduce this problem to solve a sequence of the simpler problem, which is called the min row problem. And the min row problem is the following: I give you a weight vector, which is basically the weight of each column, and then the min row problem asks for the minimum row such that the inner product between the row of the matrix and the weight is minimized. So that's the min row problem. And the key theorem is that, well, you can obtain the 1 partition approximate solution to this covering LP by solving a sequence of this problem for m log m over epsilon square iterations. Now, the proof itself is also not very difficult. I also highly recommend you to check Omri's talk on the dynamic graph workshop that talk also the same LP topic, and then he provided elegant one-slide proof of this theorem. But for us today, it's only the goal is to compute this fast enough. So we will focus on what is the min row problem in our setting, and then how far can we solve it. Any question on this part? If no, then okay, good. Next, I'm gonna give you one example of how to use this framework, how to use this framework to describe the min row problem of kECSS LP. Meaning that the KH connected spanning multi-subgraph. So it's the same thing as kECSS LP, but there is no block constraint. Okay, and then you can write this matrix A as a cut and edge incident matrix. And what is the min row problem in this case? So for example, so the cut incident matrix, you can see like C1 represent one cut, and then it incident on which edge, and so on. And the min row problem is the following: that I give you an edge, I give the weight function on each edge, right? And then ask for the minimizing row here, a minimizer row here, which corresponds to the min cut problem. So basically, if you look at this LP and then you look at it in this format of min row problem, then the oracle problem here is the classic global min cut problem. However, if you want to solve this kECSS LP, it cannot quite do that directly because of the annoying block constraint over there. That makes the problem not really a pure covering LP. If you want to do this in all settings, we need a pure covering LP. And then there's a standard way to get around this box constraints by adding the extra inequalities, also known as a Nassau-Cover inequality, which is a very generic technique. But to be specific for our setting, so we strengthen the LP in the following way. First, so look at the cut. Like for each cut in the constraint, we add the redundancy. We add the following: pick any subset of the edges inside that cut of size at most k, and we're gonna, because we want to remove the box constraint, we're gonna add the constraint in a way that we force the solution to pre-purchase the set of edges f. By already f of them, I will force the solution to pre-purchase that, so that the remaining part you need to satisfy k minus f. And I do that for all the subset of size k inside the set f. By doing that, we can get rid of the upper bound constraint, because the constraint here kind of enforce you not to pick the larger one. And we can rewrite this constraint in this form, and we can ask the same question. We can ask the same question now. What is the Oracle problem of this kind of pure version of this kECSS? So now we can write this in terms of the cut free incident matrix, where each row corresponds to a cut and a set of the free edge. When I say free edge, it means that there's the free edge set inside that cut. So now it's a cut and free edge that incident to an edge matrix, right? And it's a standard fact that you can solve this. It's enough to solve this pure covering version. And okay, what is the mean row problem? Now, it's also instructive to take a look by inspection what would be the constraint matrix of this strengthened version of the LP. So let's fix the cut, fix some cut that contain 3 edges, for example. So in the matrix A, the cut incident matrix would look like this, that have 1, 1, 1 on the first 3 columns. And if I add, let's say, the free edge, if I add 0 free edge, it means that I need to satisfy k, right? So I get the first column that is 1 over k on the first row. And then in the next row, I could also make each a single edge free. When I make a single edge free, meaning that I don't need to worry about to satisfy one of the edge, and then I need to satisfy less than k in k minus 1, and so on. And then this keeps happening for like 1, and also for all pair, for all 2, and also on. Okay. Now, looking at the formula for the mean row problem, you just look at this matrix A with adding the new constraint, and look at the weight function of each edge, right? And mean row problem asks for minimizing the inner product between this constraint matrix and the minimizing the row of the matrix and inner product of the row matrix and the weight, right? And then mean row problem turns out to look like the following function, that you want to minimize or overall cut, and then each cut you allow to kind of ignore up to f edges, and then f here can be at most size of at most k minus 1, and then you need to also normalize by k minus f. And here, when I denote ws, it means the sum of the weight inside that set. The upshot is that this is the new mean row problem in the kECSS problem. So we get this expression, which we call the normalized free cut problem. And notice that in the version of kECSM where we don't have the box constraint, the mean row problem is just simply a mean cut. But now, if you have to deal with a box constraint, the mean row problem becomes this normalized version of the free cut problem. So the upside is that there's a technical challenge that if you remove box constraint, apply this multiplicative weight update framework on this covering LP, then you get this normalized free cut problem. So any question at this point? Okay, very good. Now let's spend some time and trying to understand what this normalized free cut problem a little bit more. So what do we know anything about in the literature? So what do we know so far? So one thing to think about is that look at this cut. So you look, the denominator means that you can fix, let's say fix a cut C, right? And then the denominator means that you can ignore up to k minus 1 edges. So basically you should ignore the most expensive edges in there. But when the more you can ignore, the less normalizing factor that you have, right? And in other words, you can also write this problem, rewrite this expression by the following way. So I define lambda I to be the min cut with I edges being removed. So we can, let's say you can remove I edges, and then this is a lambda I. I call this I free min cut, okay? Now you can also rewrite this expression to be the min row problem to be like the minimum between lambda I over k minus k minus I. So basically, if it's a minimum between the normal min cut and normalized by k, or you ignore one edge but you normalize less, or up to the k minus 1. Okay, and how fast can we solve this problem? What is the complexity? So is it even polynomial time solvable? Right. So this is a question to look at. And so let's imagine that I want to compute lambda I. How do I compute lambda I, right? So basically, I can do the following way, that I can do like and choose I. Basically, to compute I free min cut, the way one brute force way to do is to select look at the graph, remove I edges from the graph, and compute min cut, right? And then you can do that and choose I time, and then you get like call of min cut. But I mean, but if you need to do all of that, then it's gonna be like M actually, yeah. And if you do all of that, this is like would be exponentially many calls of min cut. So this is not the right strategy. And it turns out that computing lambda I is also known as the connectivity interdiction problem, where it is known that you can compute it in polynomial time, mn to the 4. And therefore, if you plug in this result by Saint-Clausen, we can also show that, well, you can solve this in kmn to the 4. And that the technique there is based on some cut enumeration problem. But for our purpose, we need much faster than that. And we also need to be able to maintain this cut as well. So this seems to be a very, very difficult problem. And the main result of this paper is that, well, this min row problem is not that difficult, in a sense that it's actually, we can reduce this to the min cut problem, actually. So this, the main technical results in this work is that we show that we can solve this min row normalized min cut problem by the reduction to polylogarithmic many of them of the min cut. And furthermore, the technique also works for even the dynamic setting. The reduction can be done also in the dynamic. Basically, the main dynamic min row. Another result is that we can maintain it dynamically under the weight increase of the multiplicative weight of the framework. And then the total time is still the same as the dynamic min cut problem in the Thekoli and Conrad in the that they provide for kECSS problem. So now I will get a little bit technical on this part, how to give you a sense of how this can be done on the static version. So now I will explain how to do this, and then I feel like it's a very simple trick. So let's say that we focus on the following problem. I have a weighted graph, and then I want to output this normalized min cut, like in near linear time. And I want to output one plus epsilon approximation. So let's set some notation a bit. So first, denote that opt is just the optimal value of this min row problem, the normalized min cut problem. And now let's say that we can guess the value of this opt up to 1 plus epsilon. So let's say that row, this is the guess value that is exactly 1 plus epsilon opt. Then I define the weight function in the following form to be the min for each edge. I just truncate that. If it's exceed row, then I will just set it to row. Otherwise, I will just set a normal weight. So basically, just do weight truncation and by row. Okay. And by doing this, the key structural property is the following. So take a truncated weight and look at the minimum cut. The key claim is that you can always find a free set of size k at most k, such that the value, the more normalized value, is 1 part epsilon approximation. And then if this lemma says that, well, it's enough to just solve min cut, and then you can find the free set automatically inside this cut. So given this lemma, then the algorithm is very simple. Just find the min cut, find the optimal f star, the optimal free cut, and then that's the deduction to the min cut. Okay. Next, I'm gonna explain why we should expect this lemma 1 to happen. Actually, I will even give a full proof of lemma 1. One question, yeah.
So this also works when epsilon 0?
If you you mean like if you okay, the question is if rho is exactly off, then will it work? Yeah, the answer is yes. So it's actually the mapping is exact. Yeah.
So this will also solve the exact problem in your time?
Well, this you mean the exact problem for the min rho?
Right.
For the at least I believe so. Yes.
Thanks.
So the mapping is exact, but the way we guess, we cannot get the approximate result yet. Thank you for the question. Okay, so let's take a look. Oh, yes.
And does it imply anything for the mean interdiction problem too, or not?
Oh, actually, that's a great question because there's a follow-up work that the technique that we use here, we actually solve the open problem in the interdiction problem as well, where there was an open problem that can you get the FP task for the general interdiction problem. It turns out that this technique can be kind of generalized and then give the faster interdiction problem. Yeah, but it's different topic. Yeah, but thank you for the question. Yeah, so basically this truncation and this one can be also used to speed up the interdiction problem. Yes. Okay. Now let's take a look at the proof of the lemma 1, and this proof is very simple. I can even write the full proof here. So let's say that the lemma says that you can find the optimal set in the minimum cut with respect to the new weight, right? So let's split into two claims. The first claim is the following: that if the weight for any cut, if you can find a weight that is smaller than k1 plus epsilon opt, then you can find the free set that we are looking for. And the second claim is the following: that the min cut satisfies that bound. The min cut with respect to that weight. Okay, so to be divided in two steps. So let's first prove the claim number 2, which is very quite straightforward. So let's take a look at the definition again. So this is a truncated weight. So the weight is like the minimum between the original weight and the threshold. Okay, and let's say that the optimal normalized min cut is of the form D and F. Okay, then we can first show that the truncated weight is at most the original weight here, because by definition of this truncated weight. And now by applying definition of being the optimal normalized min cut, this is the same as k minus f times epsilon. This is just definition, right? And also the next line is look at the next the weight of f. We also know that it's at most rho times f because, well, we do truncated, so it cannot go beyond rho. And that's by definition of rho is like 1 plus epsilon f. Now we just add them together, and then we get this mean that mean minimum normalized cut is this satisfy like 1 plus epsilon k opt, and therefore there has to be a min cut inside this weight that is smaller than 1 plus epsilon k opt, and then we are done with claim number 2. Now, now we you do the claim number 1. So now we're gonna prove the first claim. So let's let's say I fix any cut C satisfying the condition in claim number 1 where that the weight in the truncated is at most 1 plus epsilon truncated times opt. Let F be the set of heavy edges in this set. The heavy edges means that the weight is at least 1 plus epsilon opt. So I define it heavy. Otherwise, I say light. Now, clearly, this set of the heavy edges cannot have more than K, because otherwise the weight could be far bigger than this 1 plus epsilon opt. Good. So we know that there are only at most K minus 1, which is good for us. And what about the weight of the cut that is not heavy inside? If it's not heavy, it means that when you truncate, then you don't change anything, right? And then you can write this form, the second form, into the original weight, and then subtracted by the truncate weight. And now for this part, you can write rho to be 1 plus epsilon opt, and therefore I mean, this is clear, I guess. I don't. But what I want to say is that if you following each of this step, then the weight of C minus F is going to be at most exactly K minus F, this 1 plus opt, and that's the whole proof of the lemma. And yep, this at least gives you a sense that the key thing is that you just do the correct threshold, and then it basically become a minimum cut problem, and then so on. But the question for the dynamic version of the problem is the following: that maybe when you maintain the weight, when you do the multiplicative weight update, the weight can keep increase and so on. And do you need to like set the threshold differently and so on? And the thing is that and then to handle that case, we're gonna use the batch version. So let me first review the dynamic version. So now let's review the multiplicative update framework for Goemans again. Now the algorithm looks like the following. First, I initialize the weight, and somehow there's a way to initialize it. And the key point is that repeat the following, that compute approximate min row, and then for each edge inside, I will update the weight. So that's the normal framework. And the weight can keep increasing, and so on. For the purpose of today's talk, I will not deal with how to do the second step efficiently, how to do the update the weight efficiently. I just focus on how to maintain the min row efficiently. Okay. So there are two key issues that we need to be aware of. First, how to update this row and every time, and then second is how to identify the free set quickly, because the free set can be upsized up to m. So identify the free set already takes time, even if I know the optimal cut for you. So first, to handle the first part, we're gonna batch off into the range of power of I, power of f1 plus epsilon I, because in the same batch, then you can use the same threshold, and then it's gonna work out beside the same batch. How to do the batching? So this is exactly the framework, epoch-based framework of the multiplicative update. So this is at least first node that I can trace off is by Fleischer, that you can do this kind of batching for the multi-commodity flow, but it turns out to be very general batching. So the framework is the following: that you also initialize the weight in the same way. First, compute the lambda, which is the min row at the current weight, and repeat the following epochs. So you need to do this only log n over epsilon squared epochs. And how to do in each epoch? Then in each epoch, compute the min row problem, which is C and F here, and such that a normalized weight is within this range, and update the weight accordingly, and repeat, right? And then we do this until the min row has increased by at least 1 plus epsilon. and then this is the end of, and then this is the end of the epoch, and we start a new epoch. And it turns out, and then if you notice that in the same epoch, then they have the same threshold, so you can just use the same threshold throughout the epoch. So this is works very nicely. So now I'm gonna focus on how to speed up and implement in this epoch. Now the goal is to implement this in running time of linear time plus the number of cuts of that output inside the epoch. So if you can do this, then if you can do this implementation, then the total running time would be of this form, that you just sum the running time over all the epoch, and then you can show that it's gonna be nearly linear running time, because the number epoch is only log n over s1 square, but the number of the cuts that you produce in each iteration that is used is exactly the same as the number iteration in the non-epoch version. So you can charge this to the number iteration, charge the number of cuts to be nearly linear. Okay. So now I think it's clear. So now I'm gonna tell you how to do this. To do this reduction to the dynamic mean cut. Basically, we for simplicity here, let's not worry about the size of edges. Let's say that the number of edges is always bounded by polylog number edges. And we're gonna use a data structure from Chekuri and Conrad to handle the general case. So let's see how we do this. So that's okay. And then before that, there's also another issue that you can focus on, which is how to identify the best free set quickly. And then the key answer is that whenever you do thresholding, it will automatically give this free set for you by the thresholding. So this can be summarized. The thresholding is can be summarized in this mapping theorem in the following. So fix a threshold that is 1 plus lambda, and denote opt W to be the mean row optimal, and also the truncated weight here to be the truncated weight that we use. Now there are two statements. First of all, say that if as long as the mean row is inside the range, then the minimum cut with respect to that is going to be inside a certain range. So there's two space. One space is the original weight, and the second space is on the truncated weight, right? So as long as op is inside that range, then the mean cut is going to be inside the smaller range. And if the second property is that whenever you find a cut such that the weight of the truncated weight of that cut is smaller than k row, that is a good cut, meaning that you can take that cut together with the free edges defined by the set of edges that is heavy, meaning that you just take the edges that is heavy, but that has a weight at least row. Then you can show that if you give this, it automatically gives you a good free edge, and then this is a good approximate the free cut to the mean row problem. Okay. Let's see how do we use this to so basically the proof is very similar to the static case. So it's very small modification, then you will get it. So I will not present the proof here, but I will show you how to use this to implement each epoch. But basically, the algorithm is the following. So we initialize the weight, the bin row. I mean, we know let's say we are at the starting of the epoch, we initialize the weight of the bin row, and then the goal here is that we just we initialize the dynamic algorithm of by Chekuri and Conrad with respect to the truncated weight. And the goal here is the following, that we just keep listing the cut in this range. Because by the theorem, if we can list the cut by this range, we are in good shape. We will be able to find the good cut. and then we keep update the weight and repeat. So basically, it's almost a black box reduction with small control that we need to be careful. So to see how it works, like for example, so this. So let's say that at the first iteration of it inside the range, by the range mapping theorem on the first condition, we know that there has to be some cut inside this range in the second space. Because there is some cut, then you can use the dynamic data structure to list this cut. And then because this cut in this range, inside this range, you can use the second condition of the range mapping to say that, oh, this cut, you can also identify the corresponding the free edge set, and then you will get something that is close to optimal cut automatically from the theorem. And then when you do the updates the weight, this optimal value and the cut and the weight of the cut also increases a bit. And then the goal here just like keep repeating listing this cut until everything go out until the cut in the second range go out of this range, go out of the k row, and then this kind of finish of epoch, and then you can show that this simple range mapping theorem will give you all the ingredient that you need, and in here I hide all the details about how to exactly implement the reduction, but the high level of the range mapping will go along this way. Okay. So actually, that's pretty much all I want to say in this talk. So I just want to conclude here that I would love to also see more systematic theory of the fast approximation algorithm. I would love to see some more universal theory on how to do fast LP, or on more of the combinatorial optimization problem. Can we develop fast routing algorithm? Can we do the nearly linear time for 2 connected spanning subgraph? It's still unknown. We don't know how to do that in linear time. And can we solve LP for even broader class on the survivable network design problem? Can we get that faster? We also don't know. And even like, can we solve the same LP here with high accuracy in nearly linear time? It's also very interesting in my view. This is because many interactive routing algorithm needs high accuracy software to do. Yes.
So you just need one high accuracy solution, or round?
Every round, yeah. You mean for the iterative routing?
So yes, I'm just asking, like, do you need to solve one LP then, or many?
Many.
Okay.
Yeah. Iterative routing means like you solve many LP. With that, I would like to conclude my talk.
Still have time for questions. Okay, then let's thank Sorrachai again.